Hello everyone, my name is Zobnina Natalia and today we are discuss oxidative phosphorylation. Oxidative phosphorylation is ATP synthesis with electron transport chain partition. Electron transport chain or respiratory chain is located inside in the mitochondrial membrane. It includes 5 enzymes that are called respiratory complexes. The first respiratory complex, or NADH dehydrogenase, looks like L letter and is formed from the following coenzyme: flavin mononucleotide, ubiquinone, and iron sulfur cluster. Iron sulfur cluster is complex substance that contains 3 valenced iron and sulfur atoms from amino acid cysteine or pure sulfur atom at the angle of the crystal lattice. Molecular weight of NADH dehydrogenase is about 800 kilodalton. The second respiratory complex is made up from 2 parts: hydrophilic and hydrophobic. Hydrophilic part locate in mitochondrial matrix. It is FAD dependent enzyme from Krebs cycle that is called succinate dehydrogenase. Hydrophobic part includes several ubiquinols and iron sulfur cluster. The second respiratory complex is called succinate dehydrogenase and its molecular weight is 125 kilodalton. The third respiratory complex is cytochrome BC1 complex. It has molecular weight 400 kilodalton. It consists from iron sulfur cluster and several complex proteins that are corresponded to chromoprotein. They involve heme as prostatic group and 3 valence iron at the center. Cytochrome B and cytochrome C, the first, differ in radical nature near heme structure. Cytochrome C is chromoprotein 2. It is peripheral protein and it corresponded to hydrophilic type. The fourth respiratory complex, or cytochrome C oxidase, has molecular weight about 200 kilodalton and includes 2 chromoproteins, cytochrome A and A3. They contain heme as prostatic group and copper and zinc ion at the center. The fifth respiratory complex is called ATP synthetase. It consists of from 2 parts. One of them is located inside in the mitochondrial membrane and another is in mitochondrial matrix. Proton will move from substrate that locate in mitochondrial matrix, two respiratory complexes from the first to the fourth. It will happen spontaneously because oxidation and reduction potential value will increase from minus 0.3 volt at the first respiratory complex to plus 0.84 volt at the fifth respiratory complex. Respiratory chain action is explained by the chemical and osmotic theory. It was formulated by American biochemist Peter Mitchell in 1961 and was proved on practice by Soviet biochemist Vladimir Skulachev in 1975. The chemical and osmotic theory has the following position. Protons can't enter from mitochondrial matrix through mitochondrial membrane spontaneously. It happens because of movement along respiratory chain from the first to the fourth respiratory complex. Respiratory chain works like pump for proton. As a result, gradient potential as difference in proton concentration between inner and outer sides of membrane will appear. Difference in proton concentration lead to electrical and chemical potential appearance. Sum in gradient and electrical and chemical potential is an electromotive force for ATP synthesis reaction. Now let's explain how do proton move along respiratory chain. Protons enter from substrate that are oxidized in mitochondrial matrix to coenzymes, nicotine amine dinucleotide and flavin adenine dinucleotide. Coenzymes are transferred into reduced state NADH plus H and FADH2. Reduced coenzymes enter protons into respiratory chain. So, some substrate is oxidized under NAD-dependent enzyme. As a result, reduced NADH will form. It sends two proton and two electron to the first respiratory complex and transfer flavin mononucleotide into reduced state. Reduced flavin mononucleotide sends two proton into intermembrane space and two electron into iron sulfur cluster. Electrons from iron sulfur cluster will be grabbed by ubiquinone and After that, ubiquinol will move to inner size of inner mitochondrial membrane and take 2 proton from mitochondrial matrix. Ubiquinol transforms into reduced state like ubiquinone 8,2. After that, it shifts to outside of inner mitochondrial membrane and 2 protons are pumped into intermembrane space. Electrons enter into the second respiratory complex. They are taken by ubiquinone from the second respiratory complex and 2 protons from succinate dehydrogenase. This enzyme is located in mitochondrial matrix. Reduced ubiquinones moves to the third respiratory complex to the cytochrome C the first. But cytochrome can accept only electrons. That's why 2 protons will be pumped into intermembrane space. Ubiquinol returns into oxidized state. 2 electrons from the second respiratory complex enter into iron sulfur cluster of the second respiratory complex. After that, they will be passed into cytochrome B, then into iron sulfur cluster from the third respiratory chain. After that, electrons from the third respiratory complex will be attracted by ubiquinol, and then 2 proton will be taken from mitochondrial matrix. Ubiquinol becomes reduced again. After that, it sends 2 proton and 2 electron into cytochrome C the first. Protons are pumped into intermembrane space. Electrons will enter into cytochrome C, and after that they enter into the fourth respiratory complex. It has the highest oxidation and reduction potential value. As a result, half reaction of oxygen reduction will happen at the center of cytochrome. 4 protons will be taken from mitochondrial matrix. 2 of them will be spent on water formation, and 2 will be pumped into intermembrane space. As we see, protons and electrons moves spontaneously from the first to the fourth respiratory complex. As a result, inner size of mitochondrial membrane becomes poor in electron, and outer size of mitochondrial membrane becomes rich in proton. This difference in proton concentration is called gradient potential. due to difference in proton leads to charge formation, electrical and chemical potential will form. Electrical and chemical potential in sum with gradient potential may be spent by different way. At first, it may be heat production. Also, it may be transport some ions from cytosol into mitochondrion or from mitochondrion into cytosol. But today we discuss the third way. It is transformation of electrical and chemical potential with gradient potential into energy of macroedgic bond of ATP. So ATP becomes synthesized when sum in gradient and electrical and chemical potential will be more than 0.2 volt. ATP forms with ATP synthetase. It's complex protein that is made up from two parts or two subunits. Oligomesin dependent subunits FO that locates in a mitochondrial membrane, and F1 subunit that is in mitochondrial matrix. FO subunits includes C subunits that are made up from acidic amino acids and A subunit. F1 subunit is made up from 9 subunits: 3 alpha, 3 beta, delta, gamma, and epsilon. Gamma subunits join oligomesin dependent subunits and F1 subunits like road. When sum in gradient and electrical and chemical potential will reach 0.2 volt, proton channel will open inside oligomesin dependent subunits. Protons return from intermembrane space to the mitochondrial matrix. When protons are returned into mitochondrial matrix, they make FO oligomesin dependent subunits turn around its own axis. F1 subunits will be turned around together with FO subunits. As a result, alpha and beta subunits inside F1 subunits will change their location in space. As a result, electrical energy that is carried by protons will be transformed into energy of chemical bond in ATP. So let's explain in movement. So here we can see situation where when inside size from mitochondrial membrane, concentration in proton is low, and outside from mitochondrial membrane, concentration in proton is high. So ion channel is open inside oligomesh-independent subunit. It begins to turn around its own axis. As a result, F1 subunits will turn too. Alpha and beta subunits change their location in space. Alpha subunits contain basic amino acids, so it kept ADP with hydrogenose bond. When gamma subunits will turn around, alpha and beta subunits becomes close in space. Let's look again. So ADP is kept by alpha subunits, then gamma subunits is turned around, and phosphorus residues is added to the ADP and ATP forms. There are 3 points where required potential for ATP synthesis may be reached. It is near the first respiratory complex, near the third, and near the fourth. So if proton movement will begin from an AD-dependent enzyme, we enter or we go through all 3 points where ATP may form. If proton movement will begin from FAD-dependent enzyme, we go through 2 points where ATP may form. That's why we may characterize respiratory chain walking. It may be present by the following characteristic. The first is phosphorylation index. Phosphorylation index is amount of phosphorus acid residue that were spent on ATP formation per 1 absorbed oxygen atom. For full chain, it equal about 3. For short chain, it equal about 2. Phosphorylation index may be calculated by another way. It happens because 1 proton is lost for ATP transport from mitochondrion into cytosol, and 3 protons are lost when phosphate residue is transported from cytosol into mitochondrion. During full chain, 10 protons will be pumped into intermembrane space. 4 protons are lost. So that's why phosphorylation index will be calculated as a ratio between 10, 4, 4. And in result we have 2.5 ATP. A long-short variant of respiratory chain 6-proton will be pumped into intermembrane space. 4 protons will be lost. Phosphorylation index will be calculated as a ratio between 6 and 4. As a result, we got 1.5 ATP. ATP production depends on several factors. At first is rate in oxygen entrance inside mitochondrion, or respiratory rate. Oxygen is acceptor for proton, so if oxygen enter in mitochondrion actively, oxidation reaction in mitochondrial matrix will increase and proton will enter in respiratory chain active too. As a result, ATP formation will increase. When oxygen entrance will be decreased, oxidation reaction rate will decrease too, and ATP formation will decrease. Dependence between ATP formation and substrate present is directly. Also, ATP formation depends on ATP and ADP ratio, or ratio between work and rest. So when cell works, it means that ATP is spent actively, and ATP level decreases, ADP level increases. Due to ATP level decreases, it makes oxidation reaction speeds up. As a result, ATP formation will increase. When cell accumulates some amount of ATP and transfer into rest state, so ATP level will high, and it will have increased level of reduced coenzymes. As a result, oxidation rate reaction will decrease and ATP production will decrease too. This mechanism, when ATP production depends on oxygen entrance and ratio between ADP and ATP level, is called respiratory control. ATP production depends on some substance presence. Several substances may decrease ATP production because of violation in proton transmission from one respiratory complex to another. They are inhibitors. Rotenone and Babbich's are inhibitors for the first respiratory complex. They block electron transmission from iron sulfur cluster into ubiquinone. Malonic acid is inhibitor for the second respiratory complex. Malonic acid is competitive inhibitor compared to succinic acid. That's why succinate dehydrogenase of the second respiratory complex will be inhibited. Carboxyne and antimycin and British antiluazide are inhibitors for the third respiratory complex. Fungicide carboxyne blocks the third respiratory complex on level of cytochrome B. Antimycin is metabolite of some bacterial, and as British antiluazide blocks electron entrance into cytochrome C the first. Carbenoxide, hydrogen sulfate, hydrocyanide are inhibitors for the fourth respiratory complex. They form coordination compound with copper and zinc ions that are located at the center of cytochrome A and A3. As a result, respiratory will be blocked and ATP production will be blocked completely. Oligomycin is inhibitor for the fifth respiratory complex. It blocks proton transmission from intermembrane space into mitochondrial matrix. Uncoupling is decreasing in ATP production without violation of proton transmission along electron transport chain. It may happen because of decreasing in gradient or electrical potential. Substances that decrease electrical potential are called ionophores. They increase entrance of positively charged particle inside mitochondrion. As a result, difference in positive charge between inner and outer sides of inner mitochondrial membrane will decrease, and potential that is required for ATP synthesis will not reached. Ionophores are some medicines like valinomycin, nigericin, and bilirubin. Substances that decrease gradient potential are called protonophores. Such substances like fat acids, adrenaline, thyroxine, and derivatives of phenol are corresponded to protonophores. Let's explain how do protonophores work on example of 2 and 4-dinitrophenol. 2 and 4-dinitrophenol is derivative of aromatic hydrocarbon. It has lipophilic nature and low acidic properties. Nitro group present increases acidic properties, and when dinitrophenol loses proton, negatively charged particle will form. It enters inside mitochondrion spontaneously and take proton from intermembrane space. After that, it return proton into mitochondrial matrix, missing ATP synthetase. As a result, required gradient potential for ATP synthesis will not reached. It will lead to increasing of oxidation reaction inside cell. But ATP will not form because required gradient and electrical potential will not form. Accumulated energy will spent on heat production. Thank you for your attention. Wish you all the best.